So we'll continue our discussion on chromatic dispersion or group velocity dispersion that we started last time. And so we saw last time that it can be considered as a contribution of material dispersion plus waveguide dispersion, right? And then we saw how material dispersion comes about because of the refractive index dependence with wavelength of the material, which is silica glass in the case of optical fibers. So today let's look at the other contribution, which is waveguide dispersion. Right. So this, as we discussed, is purely due to the waveguiding effect. Right. It's basically as you change the wavelength, the mode profile traveling through this fiber changes slightly. Right. So the confinement of the mode in the core and cladding changes slightly. Even because of this change in the relative proportion of power in the core and cladding, basically the effective index of the mode, right, which lies between the core and cladding, that changes a little bit with wavelength, leading to different group velocities for different frequencies of wavelength, right? Even though, even if you consider the refractive indices of the core and cladding to be constant. So we had written down this expression for the waveguide dispersion, right? So this is a function of, so this is the capital D parameter, dispersion parameter that we introduced last time, right? So from the waveguide contribution, so we saw again, we can write it like this. Okay, so here, so last time we had two terms, right? One was sort of the material dispersion, which was directly the sort of the second derivative of this refractive index of glass with respect to wavelength. And then the second term was this, right? So it depends on this index contrast, normalized index contrast, and then this variation of this this normalized propagation constant small b, right? So the BV curve, the B is the normalized propagation constant, and B is the normalized frequency, right? So these BV curves are universal for a particular type of waveguide, right? So for a step index fiber, we have these universal BV curves, right? So we can basically compute this factor here for any step index fiber, right? And then we can easily compute the waveguide dispersion just from the like these parameters. This is also, we know, right, for glass, what is the refractive index. Other numbers here are constants. So, right. So just to remind you, this normalized propagation constant was defined like this: effective index of the mode minus the cladding index divided by the difference in the core and cladding index, and the V parameter was defined like this, where A is the core radius, right? Right, so if you look at a step index fiber, so we get these universal curves, VV curves, right, for different modes. And again, since basically we are only interested in single mode fibers because they are the ones in use for telecommunication system nowadays. So we are looking just at the lowest order, also called LP01 mode. Right, so if we plot this normalized frequency on the x-axis, then let's put some numbers on the y-axis here. Right, so the small b lies between 0 and 1, right? So Small b sort of goes like this. Right, as you increase v number, so as you, for a given fiber, if you decrease the wavelength or increase the frequency, the mode gets more and more confined into the core, and this v parameter increases, right? And it approaches 1 for very high v numbers. So again, recall that sort of the region of interest for us for communication systems is basically this region sort of between 2 and 2.4 or 2 and 2.5, right? So 2.4 is the single mode cutoff, right? Beyond which, like if you plot for the next higher order mode LP11, so that will start from 2.4 here. So for single mode fibers, we are below 2.4, and in the telecom range of wavelengths, we are typically between 2 and 2.4. So this is sort of the region of interest here. Okay. So now, so from this curve, right? So this is B, right, as a function of B. So from this curve, we can compute this quantity, right? So multiply B with V and then take the double derivative. So since we know B for every V, we can compute this also numerically, right? So that curve looks like this. Okay, so this is this quantity. V times the double derivative of B into V divided by the dispersion. Right, so one thing to note here is in the region of interest, it's always positive, right? So actually, if you keep extending the range here, it actually goes negative. So for V greater than 3, it goes negative. But for our region of interest, it's always positive. And if you look at this region of interest here, right, it's sort of monotonic decreasing function like that. Right, and if you look at this expression here, D, so there's a minus sign in front, so all these are positive quantities. There's a minus sign in front here. So if this quantity is positive, that means the waveguide dispersion parameter is negative, right? So for this range, telecom wavelength range, so roughly let's say between 1.3 and 1.6 micron, the waveguide dispersion is negative. Right? So this is for like a simple step index fiber, right? Okay, so in this range, so if B is between like roughly 2 and 2.4, that corresponds to sort of a wavelength range, let's say between 1.25 and 1.65 micron. Right, in this range, D is always negative, so if you pick a typical conventional single mode fiber, the waveguide dispersion is about like -2 to -5 picosecond per nanometer cloud. Okay, you just put in the numbers here. Right, and if you recall the material dispersion, which we discussed last time, that was positive for wavelengths above 1.3 or 1.27 micron when it crossed 0, right? So you can see that the waveguide dispersion is sort of opposite sign to the material dispersion for the telecom range wavelengths, right? So it can be used to compensate the material dispersion, right? And so the overall dispersion, when you add the two, you can sort of tailor it based on the type of fiber you design, because that will decide the waveguide dispersion. The material dispersion is fixed, right, from the property of silica. Yeah, right. So in this range, it's also very easy to sort of compute what the exact dispersion value is, right? So recall we had this empirical relation for B as a function of B. So it was something like this, right? So in this range of B between 2 and it was even valid for slightly bigger range, but anyway, it's valid for this range, right? So these were two constants. This was like I think 1.14 something, and B is like 0.996 or something, right? So you can use this sort of empirical expression for B and then compute this exactly, right? You can plug B in here, and then it's a function of B only. So if you plug this in and do that, you will see that basically this is just depends on this constant B. Right, so for any V parameter or any wavelength here, you can calculate this value exactly from this expression and then calculate what the dispersion is. So if we plot the total dispersion, adding the material and so yeah, the total dispersion is the sum of the material plus waveguide. Okay, so if you look at that, okay, so this is D again picosecond per nanometer kilometer. And let's say here is wavelength in micron. So recall the material dispersion looked like this. So it crossed 0 just below 1.3 here. Right? To take pure silica, about 1.27 crosses 0. Okay, so that's the material contribution that we saw last time. Right, so it's normal dispersion below 1.3 and anomalous dispersion or positive D above 1.3. And this waveguide dispersion you see here is always negative, sort of, right? So, and the value you can see is sort of in this range, so it looks something like this. So this is the waveguide contribution. So now you can see when you add the two, right? So you're sort of adding a negative number to the material, or equivalently subtracting a small quantity from the material dispersion. So it shifts right down a bit. So okay, it looks like that. This is the total dispersion. Okay, so this is for like a standard or conventional single mode fiber, right? So it's a step index fiber, again with delta, let's say around 3 to 5 times 10 to the minus 3, so 0.003 to 0.005 in that range, right? And the core size A is about 4 to 5 micron radius. That's a standard single mode fiber, right? So that has a dispersion profile like this. Okay, it crosses 0 just above, so this the total dispersion crosses zero about 1310 nanometer. Right, so the material dispersion cross zero at around 1.27. Right, then because of the waveguide dispersion, this shifts a little bit. Okay, but again, so you can see in the range of operation, right? So again, so this is the telecom range of wavelengths here, right? So let's say 1.26 to 1.65. So in this range, right, it's near zero at around 1.3, and then it's always positive for most of the range. Right, and around the most popular wavelength, so 1.55 microns, this value is about sort of between 10 and 20, so roughly 15, usually 15 picosecond per nanometer kilometer. Right, so this is the wavelength with the minimum loss, 1.55. So there the dispersion is about 15 picosecond per nanometer kilometer. Right, so from this dispersion profile, if you want to calculate sort of what is the this again maximum possible figure of merit, which is sort of the data rate multiplied by the link length that I can have, right? So again, if I plot that over this sort of wavelength range here, so you can see that the dispersion crosses zero. So again, recall this expression that we had, right? So this bit rate times the transmission distance was bounded by 1 over this dispersion parameter times the source bandwidth in wavelength units. Right, so you can see that this quantity scales inversely with D. Right, so you can see, so when D is minimum, so around 1.3 it crosses zero, that's when this quantity will be maximized. Right, so if you plot, again, so this quantity B times L, so this is gigabit per second kilometer. Right, x-axis is the same scale as this axis, wavelength. Put some numbers here. So you can see that it will be max this B times L will maximize around 1.3. So
Here D is total dispersion.
D is total dispersion, yes. Right. Okay, so these three different curves are for different delta lambda. So this one is delta lambda 2 nanometer, which will be like a standard semiconductor laser diode. This is like 10 nanometers, which could be like a bad laser diode or what is known as a superluminescent LED. And then if you use a standard LED, it's like 40 nanometer bandwidth then. Okay, so this data rate times the distance is maximized where the dispersion is minimum, and what that value is depends on, of course, delta lambda. Right? So smaller delta lambda is better. Right. So now we can also, so you can see here, for example, like if you want to operate at sort of this minimum loss wavelength 1.55, that's, you can see, away from the optimal point in terms of dispersion, right? So the data rates that we can get at 1.55 limited by dispersion is much smaller than what we could get at 1.3, right? So for long haul links, we would want to use wavelength because of the lower loss, but you can see that dispersion limits. One way to tackle this is using what are known as dispersion shifted fibers, right? So again, this waveguide dispersion depends on the fiber parameters, right? So it depends on this BV curve, which we basically get from solving the modes, right? So basically it depends on, for example, these parameters: core size, index difference, right? So by modifying sort of the index profile and the core size, etc., you can modify this waveguide dispersion part, right? And so equivalently shift the total dispersion to a different. So for example, you can shift the zero crossing to a different point, or make the shape look slightly different, right? Depending on if instead of just the standard step index fiber, if you go to sort of slightly different designs. Okay, so for example, like okay, so if you look at the standard single mode fiber, so this is the most widely deployed and cheapest available fiber. Right, so this, if you look at the profile, right, of refractive index versus sort of a radial distance, then so the core diameter here is about 9 micron, right? This is N1 and N2, and this normalized index difference here, delta is about 0.35%, right? Or 0.0035 is delta. Right, so I'm plotting N versus radial distance. Right, so that's the standard single mode fiber we've plotted here. You can get what is known as a dispersion shifted fiber, DSF. Right, by just changing the core size and this index contrast a little bit. Okay, so again, so here, if you see this waveguide dispersion scales with this index contrast. Right? So let's say I want to shift this zero dispersion point to higher wavelengths, right? So I want to use higher wavelengths, but I want to lower the dispersion there. So one way to do that is if this waveguide dispersion was more negative, right? So that will shift this material dispersion more down. So the total dispersion will shift more towards downwards and to the right here, right? So the zero crossing will move towards the right. And you can see that I can increase or make the waveguide dispersion more negative by increasing this quantity delta. Right, so this dispersion shifted fiber basically increases the core cladding index contrast. So you increase this by basically roughly 4 times. So you go to about 1.2%. Right. Also, the core size is decreased a little bit, or roughly halved again. Okay, and so yeah, so the zero dispersion wavelength for standard single mode fiber is about 1310 nanometer. So with this kind of profile, you can shift the total zero dispersion to longer wavelengths near basically the wavelength we want of 1.55. Right. So using this kind of fiber, I can get both minimum loss at 1.55 and also minimum dispersion at 1.55. Okay. So I can really, so basically these curves will shift to 1.55. So there's a question, a good question that, so there's a particular wavelength here where dispersion is exactly zero. Right. So from here you would think, okay, so then what does that mean? This should shoot up to infinity, right? There should be no limit on the data rate. Of course, physically, you can imagine that should not be possible, right? And basically, what starts happening is that, so when you're here's this, so recall this B was nothing but the second derivative, right? Or equivalently, remember there was this quantity beta 2, which is basically just D scaled in different units. Right, so that was second derivative of this propagation constant with respect to frequency. Right, and we basically did this by saying, okay, the pulse spreading was basically the propagation time as a function of frequency or wavelength. Then we take the derivative with respect to wavelength and then this, right? But you can imagine if this is some sort of Taylor series kind of expansion, right? There could be higher order terms here. I could take the second derivative and multiply by delta lambda square, right? So here basically what's happening, the first order term 0, so then the second order term starts contributing. Okay, so what you get is higher order dispersion, or the next order dispersion will be third order dispersion. Okay, so we'll briefly take a look at that in just a few minutes. So yeah, so this doesn't shoot up to infinity because now third order dispersion starts limiting you. So the second one. Okay, and then you can play more games like this. So you can make like fancy profiles. So for example, okay, you can have sort of like multiple core regions or something, more complicated profiles like that. Okay, so it's high index, then low index, and then another slightly higher index. Right, so there's like a ring of, so this looks like high index, then a ring of low index, and then your clad. Right, so about 0.75% here. About 0.45%. The inner core here is about 6 micron diameter. The outer core is about 9.5 micron. Okay. So now basically what with these kinds of profiles, what you can do is you can change the shape itself. Right. So with these step index fibers, basically the shape remains like this, right? Sort of monotonic increase, which is decided by the material dispersion. And the waveguide dispersion is sort of like a almost constant negative number that you just subtract. But if you go to other kinds of profiles like this, you can change the variation of the waveguide dispersion and so change the shape of this. Okay. So for example, if you want to do some WDM kind of application where I use multiple wavelengths over this entire band, right, then I would want my dispersion to be sort of low and flat over this entire range, right? Otherwise, I'll have to compensate for different dispersion for different wavelengths, right? Which can become a problem. So this kind of fiber is known as a dispersion flattened fiber. Okay, so basically what you can get is like a very low value of dispersion, so less than like 3 picosecond per nanometer kilometer over the entire telecom range. So 1.3 to 1.6 micron. Okay, so if I plot on this scale itself, so this is conventional fiber, right? So maybe let's create some things to make some space here. Okay, so that's how the total dispersion looks like for the standard single mode fiber. If you look at this dispersion shifted fiber, basically it shifts this towards the right. So it looks like this, crossing 0 around 1.55. Okay, so this is dispersion shifted fiber. Right, so this is useful if, let's say, you are using the C-band wavelengths around 50 nanometer, then you can get both minimum loss and minimum dispersion. But it's still not suitable for wideband applications if you want to use the entire telecom range. So if you look at this dispersion flattened fiber, that sort of looks like this. Okay, so it has a very low value of dispersion over this entire band. But of course, these more fancy fibers are more expensive, more difficult to make, right? So the standard single mode fiber is the cheapest, so it's the most widely laid down fiber also. But what you can also do is like, so your main part of the link, there are other kinds of fiber also. I mean, that it's not just these three. There are multiple. You can really play with these profiles, right? So there is something called dispersion compensating fiber, which is even more shifted. It's sort of like looks always negative, normal dispersion like this. Okay, so that's called dispersion compensating fiber. Right, so basically what you can have is like, so your most of the long distance part of the link is standard fiber, right? And then near the receiver part, you can lay down some few meters or few kilometers of these other types of fiber to compensate for the dispersion, right? So for example, so let's say at 1.55 micron, your standard SMF has positive dispersion here, right? And basically we saw that the broadening goes as the dispersion coefficient times the length, right? So you can calculate what this D times L is, and then lay down a dispersion compensating fiber just before your receiver, which has opposite dispersion, and then you can calculate what length of dispersion compensating fiber you need, such that sort of D1 L1 plus D2 L2 is 0, so that the total broadening is compensated. Okay, so that's one way to sort of compensate for dispersion, is laying down different fibers with different dispersion profiles, such that when you add all these different fibers up over the link, the total dispersion comes out to be 0, weighted with the length. Okay, so let's briefly go back to this question that, so what if D is 0, right? So let's say, right, I'm operating at the wavelength where this D is almost exactly 0. So then can I just boost up my data rate as high as possible? There is no limit. So answer is no, of course, because of now the higher order dispersion starts coming in. Just a word about higher order dispersion. Right, so you can see from this curve, D is also a function of wavelength, right? So D is not constant, right? D is also a function of wavelength, which immediately tells you that there is also higher order dispersion, right? So there is a slope to the dispersion, right? So if I define a dispersion slope S, which is a derivative of the dispersion parameter with wavelength, right? It's sometimes also called differential dispersion parameter. Right, so again recall D was the derivative with respect to wavelength of this 1 over group velocity. Right, and it was related to the second derivative of beta 2 was second derivative of the propagation constant with respect to field. So now at this point where D or beta 2 is 0, right, you can see that this slope is not 0, right? So at this point this D of capital D by d lambda is still non-zero, right? So that's the next order term I was talking about, right, in the Taylor expansion. So that's called third order dispersion, right? Dispersion slope is coming about from third order dispersion. The dispersion parameter is coming about from second order dispersion, also called group velocity dispersion, because we are looking at the dispersion of the group velocity. Right, so this comes from third order dispersion. So you can see that this will be, so I'll have to take another derivative with respect to lambda, right? Equivalently, another derivative with respect to frequency. So that will be proportional to beta 3, right? Third order derivative. So S here, right? So if you compute this, you'll get S equal to so beta 3 right. So this S in general depends on beta 3 and beta 2. So this is the third order dispersion, right? So this was the GVD parameter. Beta 3 is the third order dispersion, which is the third derivative of beta with respect to field. Right, so in general, this dispersion slope depends on both beta 3 and beta 2, but if you're at a wavelength where beta 2 is 0, then it will depend on beta 3. Right, so you can see here, if I have a source if I use a transmitter with a bandwidth delta lambda, then from here basically I can write the effective D as S times delta lambda, right? So that means if I look at this bit rate times length, which was d times delta lambda. So now for d, I put s times delta lambda. So this becomes s times delta lambda square. Right. So now, if you're operating at a wavelength where your group velocity dispersion is 0, then your bit rate times transmission distance will be limited by the dispersion slope or the third order dispersion. And now it depends on the square of the source band. Okay, so this dispersion slope S you can see here, right? So for conventional single mode fibers, this D is an increasing function of lambda, so the slope is always positive, right? So its S value typically is about 0.05 to 0.1 picosecond per nanometer square kilometer, right? Because again, so D was picosecond nanometer per kilometer. So you take another differential with this lambda, so you get a nanometer square. And you can also see from here, that's why you get a delta lambda square. Okay, so yeah, so if you plot S as a function of wavelength, for this telecom wavelength range, positive with this value. Okay, so yeah, so we can estimate what is the limit now. So let's say we are working at the zero dispersion wavelength. So either using conventional single mode fiber at 1.3 micron or with dispersion shifted fiber at 1.55 micron. So then the GVD broadening due to GVD is 0. But then what is the ultimate limit on this? We can estimate. So let's say a laser diode at 1550 nanometer with delta lambda 2 nanometer. Okay, we use a dispersion shifted fiber, so D is sort of 0, S is about, let's say, 0.05 peak per second per nanometer square per kilometer. Right, so if you put the number here, this is limited to about 5 terabit per second kilometer. Okay. So yeah, so using very cheap laser diodes, if you operate at the zero dispersion point, you see you can get very high data rates. So if you operate at tens of gigabit per second, then you can go for hundreds of kilometers. If you do even better, if you use sort of single mode lasers where this delta lambda is now, let's say, picometer or less, then you can see it scales as delta lambda square, right? So this goes up to like hundreds of terabits per second. Okay, so yeah, with modern sort of semiconductor lasers, single frequency lasers, if you compensate for GVD, then the capacities that you have are hundreds of terabits per second kilometer, right? So, which is sort of, again, in the first couple of classes, we were estimating sort of the fiber capacity and all that, right? So it goes back to that. And so we still haven't utilized all of that available bandwidth. Okay, so that sort of finishes our. So of course, for certain applications, for optical communications, like if you go up to sort of third order dispersion, it's enough. But for certain other applications, like in nonlinear optics or some other kinds of applications, not maybe communication related, maybe sometimes also even communication related, you can also include higher terms, right? So you can imagine there will be a fourth order dispersion, beta 4. So with every higher order, of course, that contribution is smaller and smaller. But if the previous order is somehow 0 or very small, then you have to include the higher order. Right? So that's why here, for example, if beta 2 was 0, then we have to include beta 3. But in general, you can also include higher order terms, beta 4, beta 5. So that finishes our discussion on chromatic dispersion or intramodal dispersion, which is sort of the dominant dispersion mechanism for modern day optical telecommunication systems. Any questions on this? So if not, then we'll discuss sort of another dispersion mechanism that happens in these single mode fibers, which is polarization mode dispersion. So as the name suggests, that comes about from the polarization degree of freedom of the optical mode. PMD for short. Right. So this comes about. So if you go back to sort of again the single mode fiber, the lowest order or the only existing mode is called LP01 mode. Right. So it has sort of like a Gaussian-like intensity profile along the radial direction, and then there are two degenerate polarization possible. Right. So either let's say Y polarized or X polarized mode. Right. So for a perfectly circular core, these two are degenerate, right? In the sense that for a given wavelength or frequency, the propagation constants of both these modes are exactly the same. Right. But you can imagine that what happens when we have really long lengths of fiber is that right. So if you have a very long length, kilometers and hundreds of kilometers of length, you can imagine that it doesn't remain perfectly, the cross section does not remain perfectly circular all along the length. Okay. So you can imagine if like in a certain region, let's say the core, there are some stresses on the core, right? So of course you're laying down these fibers like underground or underwater, and then they're also bending at various points, coiled up in various points. Right, so there are various stresses acting on this fiber at various regions, and also just some manufacturing defects, right? So as when these fibers are manufactured, basically you melt this preform, which is basically a big version of this fiber, and then you just heat it and sort of pull it to make it thinner and thinner. So you can imagine that as you're pulling along the length, there might be slight variations in the core along the length, right? So these variations are really tiny, but if you exaggerate them, let's say like the core sort of looks slightly elliptical in this direction here. If you look at a certain different region, maybe it looks elliptical in a certain different direction. Okay. So basically, the fiber is not identical along the length, right? And now, if you have a slightly elliptical core, I mean, this is highly exaggerated, of course. You can imagine now. So now these two polarization modes will not be. So there's a cladding around, but these two polarization modes will not be degenerate anymore if this is now slightly elliptical, right? Because the boundary conditions will be different for these, and so the propagation constants will come out to be different. Okay, so they are not degenerate anymore. Okay, and there's a difference between, so this is n effective of the y mode and the n effective of the x polarization, right? So we can characterize this difference, which is known as the birefringence, right? So for perfectly circular core fiber, this should be 0. So for the single mode fibers that are used for telecom, this is typically about 10 to the minus 7. Okay, so you can see that's a really small difference. But over very long lengths of kilometers and hundreds of kilometers, its effect can show up. Okay. So let's first imagine, like, if you had a elliptical core which remained constant over the length, right? So basically, this birefringence is a constant number over the length, right? So in actual practice for optical fibers, what is happening is that, so if I choose a particular x and y axis, this birefringence is changing with length, right? Because this ellipticity is in different directions along the length. Okay, so basically this birefringence is not a constant, but it's a random number varying across the length. Okay. But let's first imagine a fiber with a constant birefringence, right? So then you have these two modes with slightly different refractive indices, right? So let's say I launch at the input diagonal polarization, so it has equal components in the horizontal and vertical, right? So you excite both this x mode and y mode together at the input, right? So what will happen? As you propagate along the fiber, right? So the phase difference between these two polarization modes will evolve along the fiber because they have different propagation constants, right? And you know the phase goes as e to the I beta z, right? So this there will be beta x and beta y because beta is e power over lambda times n effective. Right. So as you propagate along z, these two x and y will acquire different phases, and there will be a phase difference between the horizontal and vertical components. So at the input, if the phase difference is 0, it's diagonal, right? So as you propagate, there's becomes phase difference and it becomes elliptically polarized light. Right? At some point, the phase difference will become pi by 2, right? So when this beta x minus beta y times z becomes pi by 2, then it becomes circularly polarized, right? Right? And you keep propagating it sort of becomes elliptical in the other direction, right? And then it will become when the phase difference becomes pi, it will become diagonal in the other direction, right? So basically, the polarization will evolve as the mode is propagated, right? Due to the birefringence, right? So basically, after some point, it will go through the entire cycle and come back to its original polarization, right? So this length is known as the beat length. Basically, the length after which the polarization comes back to the input polarization. So that will happen. You can see that happen when once the phase difference becomes 2 pi, right? So 2 pi is like no phase difference. So it will come back to. So this beat length basically depends on this birefringence parameter, right? So you can see birefringence depends on the difference between the effective indices, and you can see the beat length is when this phase difference delta beta, which is beta x minus beta y times. So at the beat length when z is LB, that phase difference is equal to 2 pi, right? So you can see that this beat length is nothing but basically lambda divided by this birefringence parameter. So if for typical birefringence of 10 to the minus 7, if I take a wavelength of 1.55 micron, so this beat length comes out to about 15 meter. Okay. So you can see that the polarization is evolving on length scales of few meters or 10 meters, right? Whereas the fiber we've laid down is again kilometers or hundreds of kilometers long, right? So just from this, you can sort of see that the polarization. So we launch some input polarization, typically linearly polarized at the transmitter end, but that doesn't remain. The polarization not preserved as the mode is propagating in the fiber, right? And so not only this, so this is again for a constant birefringence, right? So what happens is that the birefringence also keeps changing along with it. So that makes the situation even more complicated, right? So if you look at a pulse, right? So again, if you have y and x polarized modes, so I launch a pulse, so which has, so let's say powers in both these polarizations and the input, right? So now again, because they have different refractive indices, also their dependence on frequency will be slightly different, right? So their group velocities are also slightly different, right? So there's there's a fast mode and there's a slow mode, right? The one which has a lower index is the fast mode. So basically, you can imagine after some length, what happens is that one of these polarizations is now ahead of the other, right? So now if I add both of these polarizations, you can see there is a broadening, right? So I have a detector here which does not care about the polarization, it just detects the total power. You can see that there is a broadening in the pulse, right? So this is basically the broadening due to polarization mode dispersion, right? So this delta T PMD is the difference in the time taken by the two polarizations. So L over VGX minus L over VGY. right? So you can also write this as, so Vg is basically d omega by d beta, right? So this is basically L times the delta beta 1 again. So beta 1 subscript 1 again is the first derivative of beta with respect to frequency, and delta means the difference, delta beta means the difference is uh, in the x and y components. So different group velocities of the x and y polarization gives rise to a pulse product. Right, so again, for a constant birefringence, you can calculate what these numbers are, right? And then calculate what the broadening is. But again, for a long haul system, basically, this delta beta is also not constant along the length, right? So you have a section, let's say of a few meters, of tens of meters, where the birefringence is constant, but then it changes to some other direction. Okay, so basically this total L that you have, you can break up into segments, and each segment has some particular birefringence, right? And it's randomly varying from section to section. Okay, so then to analyze that kind of thing, you have to use some random variable theory, right? So you can imagine this kind of thing is happening. So this is some section like L1. Then the next section happens where maybe like this is traveling a little bit faster, this is traveling a little bit slower. So maybe it becomes like that. And then the next section comes, right? So basically you have these pulses sort of going backwards and forwards, and then you integrate the effect over the entire length, right? So you characterize what is known as RMS delay. Right. So you can imagine this is some kind of diffusive process happening, right? So these different directions of this birefringence is leading to different amounts of broadening in each section, right? So if the birefringence was constant, it's like adding vectors in the same direction, right? So then basically, yeah, you just multiply the whole length with the constant birefringence. But because of this random variation in the birefringence, what is happening is like you're adding vectors in slightly different directions every time. Right, so the net effect is a vector addition of vectors at pointing at different angles. Okay, so you can imagine this is something like diffusion, right? Right, this is something like ballistic transport where everything is happening in the same direction. You add up linearly, but this is something like diffusive motion where there's a random change in direction at every section, right? And the net result is some averaging over this, right? So we won't go into the details of how this is actually modeled, right? But it's similar to modeling some kind of diffusive transport, right? So this RMS delay can be modeled as that. Okay, so this is basically the RMS delay after the total length of the fiber L. Right, so why is it an RMS delay? Again, because we are adding sort of vectors in different directions, right? So we are saying that basically, that RMS is basically taking the square, right, and then averaging over some quantity. right? And then taking the square root, right? In this case, basically you just add up all delays of all the segments together because the birefringence is constant, right? And they all add up, right? So that's just a simple summation. So that's just a linear summation. But in this case, basically this RMS or is coming because if you just sort of add them up, on average you sort of get 0 because all the phases sort of these are pointing in random directions, right? So the broadening you get is dependent on the second order quantity, which is like the RMS. Right? Okay, so yeah, again, we won't go into the details of how this is modeled, but basically, this RMS delay that you get, sort of, you get an expression something like this, where this capital L is the total fiber length. Okay, and this L sub C is known as the correlation length. Right, this is something like the beat length. Basically, it's a length over which the birefringence is constant, right? So it's a length, it's like a section of the fiber where the birefringence is constant, and then after that the birefringence changes. Right, it's the length over which the birefringence remains sort of constant. Okay, so typically this is about 10 meter for typical. If you take a conventional
Sir, what is
fiber.
delta beta 1?
Yeah, delta beta 1 is the same delta beta 1 here, right? It's the birefringence or the difference in the group velocities of the two polarizations, two orthogonal polarizations, right? So this is the same delta beta 1. So this is the difference in the group velocities of the two orthogonal polarizations. Right, so this again, so this birefringence remains constant over a correlation length. Right, so that's roughly 10 meters. It can vary on average between, let's say, a meter to a kilometer. Right, this is also not exactly the same, right? This is also a randomly varying quantity because of the random stresses on the fiber. The length over which, so each section might have a different length, but this is on average the length of each section, where the birefringence is roughly constant. Okay, so you can see that typically the total fiber length will be much bigger than the correlation length, right? Because we're talking about communicating over hundreds of kilometers, so the correlation length you can see is less than a kilometer. So for practical links, this will always be much bigger than this. But sort of this is a complete expression that you can use for any capital L and small LC. So let's look at first like the non-typical limit. So let's say if L is much less than the correlation, so very very short length of fiber. So it's basically like a uniform fiber with uniform birefringence, right? It's like uh, a short piece of fiber which has the same. There's no change in its property. So this delta beta is basically just a constant over that fiber length. So basically we should get back this expression, right? So the broadening should just be the length times this difference in group velocities or inverse of the difference in group velocity. So we can check if that happens, right? So if L is much less than LC, then this expression you can see here So this exponent e to the minus, so this quantity is much smaller than 1, right? Capital L over small LC. So we can expand this as, so basically we do e to the minus x as 1 minus x. Or we can keep one more term, x squared by 2. We go Taylor expansion up to the third term. Okay, L over LC minus 1 was already there, so that cancels out these first terms. So you can get this, so you can see this just reduces to delta beta 1 square times L square, right? So you can see delta t square is delta, right? So delta t RMS will be, okay, so this is delta t square, not the square root. Right? So if you take the square root here for the RMS delay, you can see that just comes out to be what we expect for a constant value. Right? So this is just to sort of see that the expression gives me the correct limiting result. But of course, for a practical link, this is not the case, right? It's the opposite case. So let's see what we get for that. So here basically, this quantity is very large now, right? The exponent. So basically, this e to the minus x is sort of just 0 for x very large. So e to the minus x is a decaying exponential. If you look at very large values on the x-axis, basically decay to 0. Right? So this term goes away. And then we have these terms, and now again we've already assumed this capital L to be much bigger than LC, so L over LC will be much bigger than 1. So we can neglect the 1 also. Right? So we get right, so just this term remains. Okay, so now the RMS broadening due to polarization more dispersion now. You take the square root of this. So you see here now delta t square just has one factor of capital L, the fiber length, right? So when we take the square root, we get something which is proportional to the square root of the length. Like that. Okay, so this constant, this is a constant of the fiber, right? Delta beta 1 is the birefringence in the fiber over correlation length. LC is the correlation length. So this is a constant for a given fiber. So this constant we define as d sub t, which is the polarization bond dispersion parameter. This is the PMD parameter. Okay. So you can see this has units of square root of length, picosecond per square root of kilometer, because we're multiplying by square root of length, right? To get the broadening in picosecond, let's say. So somebody has asked about correlation length, right? So it's the length over which the birefringence is constant, right? So basically the core looks the same over this length, right? Or equality, like the stresses on the fiber are the same over this length, right? So if you look at the core, maybe it's compressed in this direction and elongated in this direction, but it's the same over this correlation length. Then after this, the distortion in the core changes, right? So the next correlation length, the core is now different from what it looked like here. The compression and the elongation is in different directions now, right? But again, it's roughly constant for another LC. Of course, this exact length over which it's constant is also changing. So LC is sort of the average length of these sections. So over each of these lengths, basically the beta x and beta y are constant. Then here now beta x and beta y are slightly different. If x and y are defined as the same directions, right? So basically we're taking averages over many of these sections, right? No, so this expression we've calculated for the entire length, right? So this is the broadening that we get after the entire length. The polarization factor, the length comes into this constant, the PMD parameter for a given fiber. But what is the broadening due to PMD for a given length? We multiply by the square root of the length of the fiber, right? So the broadening due to PMD for a given fiber will be the PMD parameter for that fiber times the square root of the length of the fiber we are using, right? And this correlation length is included in this constant here. Okay, so typically the range of this PMD parameter can range from, let's say, 0.01 to about 10 picosecond per square root kilometer. So one thing you can immediately see is because this scales as the square root of the length, right? Whereas we saw that the group velocity dispersion, chromatic dispersion scale linearly with the length, right? So for long lengths, you can imagine that chromatic dispersion will start dominating because that grows faster than PMD, right? So PMD is sort of a smaller effect than chromatic dispersion, and people worry about it once you compensated for the chromatic dispersion. Then you start worrying about polarization or dispersion, and if you can compensate for that too. Again, somebody else, LC is not beat length, right? Yeah, I mean, beat length is if you had a constant birefringence fiber, then what is the length after which the polarization becomes the same as the input? Okay. Whereas here the correlation length is the length over which the birefringence is roughly constant. So yeah, they're not by definition they're not the same, but they're of the same scale for a typical single mode fiber. So the turns out that the correlation length is roughly also equal to the beat length for that amount of birefringence. But yeah. Fundamentally, they're different concepts, right? I hope that's clear. So in the early days, the fiber manufacturing was not so great, right? So you can see that this depends on how good the fiber manufacturing is. If your fiber is very pristine and the core is as close to circular as possible for as long a length, then this parameter will be small, you can imagine. Right? So basically this delta beta 1, if it's smaller, then you have a lower PMD. Right? So in the early days, this was not so good, so this was towards the higher end. But nowadays, for modern fibers, we've sort of pushed it down towards the lower end. Okay. So we can estimate. So for example, let's take a typical fiber with 0.1 picosecond per square root kilometer PMD parameter. Right. So if we take L to be 100 kilometers, you can see that the broadening will be just so 0.1 times square root of hundreds. So that's just 1 picosecond. Right. That's a very small amount of broadening, over 100 kilometers. Right. Whereas if you again calculate this from chromatic dispersion or something, this will be much bigger, more than an order of magnitude bigger probably. So yeah, so this discussion is only for one mode, right? And the two orthogonal polarizations. So single mode fiber only LP01 mode, and then the two orthogonal polarizations. If you have higher order modes also, then each mode will have its own PMD, right? But we don't worry about PMD for example, multimode fibers, because the intermodal dispersion, that's much bigger, right? That's what we discussed first. So that dominates over everything, right? So that's what we worry about. So then the next level is when we go to single mode fibers, we've eliminated intermodal. So we just have intramodal or chromatic dispersion. If we've also compensated for chromatic dispersion, right, or we were operating at like near the zero dispersion or something, then the next order effect is this polarization mode dispersion. But yeah, if you have another mode, that will also have its own polarization mode dispersion, right? But yeah, here we typically talk about just the single mode fiber. Right, so this is just a broadening of 1 picosecond. So again, if you have a bit rate of let's say 100 gigabit per second, you can see that corresponds to a bit period of 10 picoseconds. Right, so you can operate at 100 gigabit per second over 100 kilometers without worrying about PMD. Right, so this is typically the range at which you want to keep the PMD. So typically the broadening due to PMD is kept to 1/10 of the bit period. Okay. But you can see that now if I go to 1000 kilometers or higher, then this becomes now 10 picosecond, and now it can maybe start affecting me a little bit. Okay. Also, let's say so this value is for sort of conventional single mode fiber. If I go to these other kind of special fibers like different dispersion shifted fiber or dispersion compensating fiber or something, then they can also give you larger amounts of PMD. Okay, so basically, as I said, PMD people worry about if they've already compensated for the chromatic dispersion, right? Then this is the last remaining thing, and that also comes into effect only for very high data rates over very long lengths.